I don't think you had a pencil yesterday. Okay. So today's lesson is on composition of transformations, a composition. And a composition is just taking a transformation, taking some kind of transformation, and you do more than one of them. So it's composed of multiple movements. So we call it a composition. We're going to do more than one thing. Okay? So honestly, if you want colored pencils, come up and get some, because I feel like doing these in colored pencils might be best for you. I think colored pencils are helpful to see what's going on. So I'm going to pause for a second so you guys can grab some colored pencils if you want them, and then I'm going to pass out some notes. Nobody wants colored pencils? We're all going to just be blah, blah, blah. Okay, I'm good with that if you're good with that. Okay, so first one. So for questions 1 through 3, we're going to perform the stated transformation on the pre-image in different colors. Give the coordinates of the image A prime, B prime, C prime. So I get to make up my own triangle, and I'm going to look at my filled out notes because I typically try to pick one that will stay on the page when I move it all over the place. So I'm going to start with A. It's going to be 2, 3. B is going to be the ordered pair 4, 0. And C is going to be 7, 2. So let's graph that. Notice that it's everything's positive. So this whole triangle is going to live in quadrant 1. So I'm going to plot point A, 2, 3. Point B, 4, 0. And point C, 7, 2. And then I'm going to connect my vertices. Okay. Are we good with that? Okay. So the next thing that I'm going to do is I'm going to rotate it. We're going to take triangle ABC and we're going to rotate it 90 degrees clockwise about the origin. So I'm just going to put some random point right here just so we can think about it. This is the ordered pair 2, 6. If I were to spin my paper and rotate that 90 degrees clockwise, this would end up right here. This is the ordered pair 6, 2. So tell me when 6, -2, sorry. When I do a 90 degrees clockwise about the origin, oh my gosh, I can't talk today.
Yeah, flip the numbers and then change the sign.
So flip the numbers means what comes first? Y, and change the sign on the X. Y opposite X. That's the rule. We didn't try to memorize any rule. We didn't go back through our notes and look it up. We proved the rule. Does that make sense? That's what I'm talking about when I say applications. I want you to be able to identify it, right? So that means I'm going to take point A, which is 2, 3, and I'm going to make the Y coordinate come first, which is 3, and then I'm going to change the sign of the X coordinate. -2, yeah. And then I'm going to look at the point B, 4, 0, and I'm going to bring the Y coordinate first, 0, and then I'm going to change the sign of the X coordinate, -4, because that's what it says to do, right? We just showed that that's what we're doing. And then I'm going to look at point C, and I'm going to make the Y coordinate come first, 2, and the opposite of X, -7. Does it make sense what I'm trying to get you guys to understand? Okay, so I'm going to graph this one in green. So I have the point 3, -2, and this is A prime, sorry. And then I have the ordered pair 0, -4, B prime. And I have the ordered pair 2, -7, which is right here, C prime. So I did all of those movements in green. Okay. How do we feel about that? Good? Okay. So question number 2 says we're going to take triangle A prime, B prime, C prime, and we're going to reflect it in the line x equals 3. So what kind of line is x equals 3?
The line going straight to the three, like along the X, like with that horizontal, right?
It's not horizontal, it's up and down, right?
Yeah,
If it goes,
vertical.
yeah, vertical. So I'm going to draw a dashed line, and I'm going to write up here that this is the line x equals 3, because I need a reference. I need something to like look at so I can figure out how far each one of my ordered pairs are from that line. Okay, so I'm going to graph this in red. So how far is point A from the line of reflection? It's right on it, so that means it doesn't move. We're just going to rename it A double prime. How far is point B from my line of reflection? It's 3 units to the left, so that means I have to take it and move it 3 units to the right. That's going to become B double prime. How far is point C prime from the line of reflection? 1 unit on the left, so I'm going to move it 1 unit on the right. Whoops. Okay. So my new ordered pairs, well, the 3, -2 doesn't change. My B prime, double prime, sorry, becomes, B double prime becomes 6, -4, I believe, right? And C double prime becomes 4, -7. Okay. What are we thinking about that? Do you guys feel okay with that one? All right. Next thing that we're going to do is translate it. And remember, we can take each one of these ordered pairs and perform the translation rule that says we're going to do what? Subtract 3 from the x and subtract 2 from the, so I'm going to just write it right below. -3, -2, -3, -2, -3, -2. That way, I'm going to do the math, like do some creative adding or whatever, and I'm going to do that right down here. So what is 3 minus 3? So A triple prime is 0, and what is -2? -2. -4. Okay. What is 6 and -3? So B triple prime starts with 3, and what is -4, -2? -6. Is this making sense? You guys understand what we're doing? Okay, what is C triple prime going to be? 1 and what? Yeah, 1, -9. Okay, so A triple prime is 0, -4. 0, -4. So this is now A triple 1, 2, 3, triple prime right there. B triple prime is 1, 2, 3, -1, 2, 3, 4, 5, 6. B triple prime. And C triple prime is 1, -9. So it actually goes off the graph a smidge. Do you guys see that? C triple prime. And when I connect my points, A, B, C, and I'm going to do a little bit of shading so you guys can see that. Okay. That is it's called a composition. We started with a triangle and we performed 3 transformations. Okay. What do you think about that? Do you guys feel okay with that? It's easy if we break it down in steps, right? And we think about what the rules are. Okay. And I always try to show my work when I do translations, right? I like to show this because I think that that's helpful for you guys. All right. So what did we say a composition was? It's just when you perform multiple transformations to one image. Okay? You perform multiple transformations to one image. If you just perform one transformation, that's just called a transformation. If you do multiple, you have to do at least two, right? Okay. So we had this word isometry. We had this word isometry when we first started this lesson. I'm going to underline it. So we said that an isometry is just, iso means same, meter means measure. So it just means it has the same measure. It's a movement that has the same measure. So if you perform a composition of two or more isometries, meaning doing two things that preserve the congruence, same measure, stays congruent, then what are you going to have? You're still going to have an isometry. So the composition of two or more isometries is an isometry. So I'm going to write that word out. I'm probably going to misspell it. Isometry. That's how I don't spell it wrong. So it's an isometry, and I just want to write what that means. It means that the shapes are still congruent. If when I move them, they're congruent to each other, then the shapes are still going to be congruent. What is the only transformation that we've learned about that does not make the shapes congruent? We learned about it 2 days ago. It changes the size. What's that called? A dilation. A dilation doesn't make them congruent. It just makes them similar because it's a change. It's a scale, right? We scale it up or scale it down. We enlarge it or reduce it. Questions about that? Okay. So in example number 1, triangle TUV has the vertices, whatever. It's already graphed for us, so I'm not going to read them out. It says graph triangle TUV and its image after a translation along -1, 5 and a 180-degree rotation. Okay, so I know that this is just a vector rule, which means that I'm going to subtract 1 from the x and I'm going to add 1 to the 5. I know that's what this means. Okay. So I'm going to just plot a point and see if we can come up with that 180 rotation. So if I plot the ordered pair 1, 3, what's going to happen to it if I rotate it 180 degrees?
It's gonna be the same size, just different. It's gonna be, yeah.
Say again.
-3.
What is it?
-3.
-1, -3. It's going to be over here because it's got to move 2 quadrants, right?
Yeah, so it'll change the first time, but then it goes back to normal the second time, but it'll change the signs.
It changes the sign. So let's talk about that. So the rule, if I do 180-degree rotation, it doesn't matter if I go clockwise or counterclockwise. So what am I doing? How do I write the rule?
X, -y.
Opposite x, opposite y. Good job. Okay. So I'm going to erase those because, again, I just want you to think about the rule. So that means that we're going to take each one of these points. We're going to subtract 1 from the x, subtract or add 5 to the y, and then we're going to change the signs. So I'm going to start with point T, and I just do the math off to the side. T is 2, -1. Well, I'm going to subtract 1 from the x, and I'm going to add 5 to the y. So T prime becomes what? Becomes the order pair 1, 4. I'm going to take point U, which is 5, -2, and I'm going to subtract 1 from the x, and I'm going to add 1 to the 5. So U prime becomes the ordered pair. 5 minus 1 is? 5 minus 1 is?
4.
And -2 plus 5 is? 3. Okay. And point V, which is the ordered pair 3, -4. I'm going to take that and I'm going to subtract 1 from the 5 and add, 1 from the x and add 5 to the y. So V prime becomes what? What's 3 minus 1? 2. And what is negative 4 plus 5? Okay, so that's the translate part. Does that make sense? We good with that? Yes or no? Did I lose anybody? Okay, so now we're going to do that 180-degree rotation. And you guys just told me all you do is change the sign. So 1, 4 becomes negative 1, negative 4. That's T double prime. U double prime, well, the ordered pair 4, 3 becomes, pick your heads up, everybody. I want you guys paying attention. 4, 3 becomes what? Negative 4, negative 3. And V double prime, 2, 1 becomes negative 2, negative 1. So I'm just going to graph the purple shape. I'm not going to fill my graph up with a bunch of stuff if I don't need it. So T double prime, negative 1, negative 4. Negative 1, negative 1, 2, 3, 4. T double prime. U double prime, negative 1, 2, 3, 4. Negative 1, 2, 3. U double prime. V double prime, negative 2, negative 1. V double prime. How do we feel about that? Feel good about it? Okay. A glide reflection. A glide reflection. So this is a special type of reflection. It's a composition, made up of a translate. That's where the glide comes in, right? When you move something to the right or to the left, you're sliding it. So that's where the word glide comes in. And a reflection. Okay. All right. So quadrilateral BGTS has vertices, blah, 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 blah. It's already graphed for us. We're going to graph BGTS and its image after a translation along 5, 0. This means that we add 5 to our X and we don't change our Y. That's what that means. And a reflection in the X-axis. When we reflect over the X-axis, if I were to take this point right, let me make it different. If I were to take the ordered pair 2, 3, and I were to reflect it over the X-axis, what does it become? This is my X-axis. Yeah, I think that Aiden said that first, right? Yeah. So what did we do, Aiden? What was the rule? What did we do? How did we perform that? What happened to our original order pair? Keep the same, keep the X opposite Y. Okay. All right. So we're going to take each one of our points and we're going to do the math. So for B, negative 3, 4, we're going to add 5 and 0. For G, negative 1, 3, we're going to add 5 to the X, 0 to the Y. T, negative 1, 1, we're going to add 5 to the X, 0 to the Y. And point S, negative 4, 2, we're going to add 5 and 0. Okay, so what does B prime become? What's negative 3 plus 5? 2, and 4 plus 0 is just 4. What does G prime become? What's negative 1 plus 5? And 3 plus 0 is? What does T prime become? 4, 1. And S prime? 1, 2. Is that making sense? Okay, so let's do that last move. X stays the same, opposite Y. X stays the same, opposite Y. G double prime. X stays the same, 4, opposite Y, 3. T double prime. X stays the same, opposite Y, T. S double prime. X stays the same, opposite Y. So I'm going to graph that. So B is positive 1, 2, negative 1, 2, 3, 4. B double prime. G, positive 1, 2, 3, 4, negative 1, 2, 3. G double prime. T, positive 1, 2, 3, 4, negative 1. T double prime. S, 1, negative 2, S double prime. So there's my quadrilateral. Is this making sense? We feel okay about it? Okay, I'll leave that there for a second. Looks like some of you guys are still writing. Okay, raise your hand if you need more time. Okay, I see you. Are we good up front? Everybody? Nod your head if you're good. Thank you, sir. Okay. So the next type of composition is called a reflection in parallel lines. A reflection in parallel lines. And a reflection in parallel lines is the composition of two reflections in parallel lines can be described by a translation vector that is twice the distance between the two lines. So let's talk about this. If I were to take this shape, P, triangle P, and I were to reflect it over this line, however far it is away here, it would be that far away there. However far this is away, that's how far this would be away. Does that make sense? Okay. So this is P prime. But then I reflect it over another line, which is parallel. However far this is away would be that far away. This would be the same, and this would be the same. So notice that this measure is right here, and this measure is doubled right here. These two guys are the same, and these two guys are the same, right? So what they're saying is that the distance from P to the reflect over parallel lines is just a translation vector that's 2 times the distance between the two lines. Does that make sense? This is the distance from one of the lines. This is the distance from the other. We've just doubled it, okay? So 2D from the bottom. So let's just try to make sense of that. So if the distance between the two lines, we're going to say that the distance between the two lines is 2 centimeters. How could you describe the translation? Well, remember that if we reflect it, it's twice the distance. And we're going to think of that distance in terms of units. So 2 times 2 is what? 4 centimeters. And so if I write a translation vector, notice I'm moving it to the right. I'm just going to move it 4 units. That's how I could write that rule. Okay. I just move it 4 units. If I wanted to write it as a vector, how do I show that I'm going to add 4 to the x and not change the y? How do I show that I'm going to add 4 to the x and not change the y? 4, 0. Okay. Can you, we're almost done with, oh, you're leaving. Yeah. Good luck. You have a swim meet, you said? Good luck. Okay. I'll post the video, bud. All right. A reflection in intersecting lines. The compositions of two reflections in intersecting lines can be described as a rotation. Can be described as a rotation through an angle that is twice the measure of the angle formed by the two lines. So if this is 30 degrees, then the rotation from A to A double prime is twice that, which would be 60 degrees. That's what that's saying, okay? So let's look at this. It says if the measure of, so I'm going to get rid of these measurements just so we can see it. So if the measure of angle TRY, that's this guy right here, if the measure of angle TRY is 42 degrees, then what is the measure of angle ARA? That's this measure. Well, it's going to be twice that. So it's going to be 2 times 42, which is what? 84 degrees. Okay. The second question has us working backwards. If angle ARA, if this measure right here is 56 degrees, then what was the measure between the angle measure between the two intersecting lines? So we're going to work backwards. So we're going to take 56 and divide it by 2, which is 28. Yeah, half of that. I don't feel like I gave you. I don't feel like you. Yeah, you're good. Okay. Let's look at our last example. Number 4. We're going to perform a glide reflection over the x-axis and to the right 6 units. So we're going to reflect it over the x-axis and move it to the right 6 units. Okay. So what happens when we reflect over the x-axis? Change the what? What's changing? Like this point right here gets reflected and it goes down here. What changed? The sign of the Y. And then if we move something 6 units to the right, what does that look like? How do I show that? What's getting added 6 to it? X plus 6. Y stays the same. Okay. So what is the glide rule for this? Well, we write it as a vector. So 6, 0 reflected in the x-axis. That's how we write that. Okay. So let's move it first. Let's move our shape. So let's see. This 6 is going to be right here. And this is 8. And this is 4. So this is my image after I reflect it over the x-axis. And then I need to take each point and move it to the right 6. So that's going to put this here. And for, let's see, that's going to go here. -4 plus 6 is +2. -8 plus 6 is -2. -2 plus 6 is 4. And -6 plus 6 is 0. Do you guys see how I did that? I just found the x coordinates, -8, -4, -2, and -6. So this is what it looks like after we did the glide reflection. Okay. So question C says, what glide reflection would move this back to the pre-image? So what rule would make this move back to the original? So just do everything opposite. Instead of adding 6, we should. So -6, 0 reflected in the x-axis. Okay. -6, 0 reflected in the x-axis.